A new preprint just argued something the AI industry has been carefully stepping around. Enterprise adoption strongly prefers stateless retrieval over persistent agent memory, and the reason has nothing to do with answer quality. The issue is structural. Mutable memory itself creates a massive operational liability the moment it enters a regulated environment. The mechanism here is simple. Every time an agent edits its own state, you multiply the surfaces an auditor has to inspect. The enterprise barrier to autonomous agents is a system design failure. Building systems that constantly rewrite their own histories creates unmanageable operational risk. You're watching Bearded AI Guy. Today's deep dive comes out of work the human architect has been tracking on the strict divide between stateless retrieval and persistent agent memory. This conceptual layout illustrates DPM, or Deterministic Projection Memory, a framework introduced in a recent preprint by Vasundra Srinivasan. Everyone's shipping agents right now, orchestrators like Letta, Zep, and Supermemory, treats persistent memory as a required foundational layer. DPM argues the exact opposite. We are looking at a direct conflict between the industry push to give agents live, editable memory and the strict evidentiary constraints of deploying AI into enterprise workflows. The dominant memory stack across the industry operates on a continuous loop. Agents read, write, summarize, and consolidate memory as they go. This contrasts the standard loop with Srinivasan's wager, an append-only log where you edit nothing. Zooming in reveals why enterprises rely on RAG. It satisfies regulated demands with an immutable index, stateless retrieval, and a pure query function. Everything mutable memory vendors currently sell as an upgrade is simply an attempt to retrofit properties that stateless RAG possessed by default. Evaluating a memory system requires asking which specific regulatory evaluation regime matches the deployment you care about. This timeline illustrates the alternative. Instead of rewriting a journal, you keep a stack of raw receipts in arrival order. They stack up without merging. To make a decision, you process those unedited receipts once. Under the hood, the continuous update loop is entirely replaced by a projection function, taking the log, task, and budget, emitting a view in one call. Because the consolidation operator is the identity, memory literally does not exist as a distinct runtime object until the exact moment of that projection. DPM eliminates intermediate memory states entirely, removing the primary vector for data mutation in AI agents. Every time you rewrite a journal, something gets lost or remembered differently. Do that 80 times, and you are no longer sure what originally happened. Technically, every single state update in a standard architecture is a distinct, separate LLM call. Each call introduces residual non-determinism into the record. This pipeline flowchart lays out the actual cost. On the LongHorizon-Bench, the summarization baseline requires 83 to 97 separate LLM calls per decision. DPM takes 2, one projection and one decision. Shrinking the node count compresses the entire problem. The audit surface, the replay surface, and the multi-tenant isolation surface all collapse down to that single projection step. Minimizing LLM calls during memory updates has very little to do with latency. It is an exponential reduction in corporate liability. When memory budgets are generous, DPM and the best stateful baseline perform virtually identically. That loose budget masks the inherent structural flaws of stateful systems. Squeezing the budget to a 20x compression ratio fractures performance. DPM's precision and reasoning coherence rise sharply. In a zero-temperature determinism experiment, running a full memory hash across 10 replays showed DPM produced exactly 6 unique hashes. DPM does not completely eliminate back-end non-determinism. LLMs still vary, but it successfully compresses the replay surface from dozens of unpredictable steps down to a single calculable call. When operating under highly constrained, zero-trust enterprise budgets, DPM provides a mathematically defensible architecture. The industry argument isn't split between a pro-memory camp and an anti-memory camp. It is a strict disagreement on the core purpose of memory itself. Orchestrators like Mem0, Zep, Letta, and Supermemory view memory as a continuous, stateful substrate, designing systems explicitly for agent learning and long-term user personalization. The evidentiary camp looks at the operational fragility of always-on persistent systems. Zepp's scaling incident in late 2025 demonstrated exactly the type of infrastructure risk DPM avoids. Your team's definition of memory depends entirely on whether the agent's primary goal is learning user behavior or providing a transparent, reconstructible audit record. The final mental model to walk away with is strict. Memory architecture must be sorted by operational workload, not by performance benchmarks. If your agent operates as a copilot or a recommendation engine, where maintaining a continuous, personalized state with a user is required, stateful memory is the correct choice. This spectrum maps the divide. When your workload shifts to the right side, where an agent possesses actual decision rights to deny credit, approve an insurance claim, or trigger tax workflows, the math changes. The moment an agent triggers a regulated workflow, statelessness ceases to be a minimalist design choice. It becomes a mandatory operational control. If this kind of architectural teardown is what you're here for, hit subscribe on Bearded AI Guy so the next one lands in your feed. Drop a comment telling me which camp your deployments align with: mutable memory as a first-class layer, or event logs and late-bound projection. Keep this rule in mind for your next system design. When agents make regulated decisions, memory transitions from a feature into strict legal evidence. Design it that way.